Welcome back to HPC, or good evening as the case may be, depending on where you are in the world. My name is Douglas Thane from the University of Notre Dame. And each year, HPDC selects an annual achievement award to recognize a researcher who has made a significant impact in the design, evaluation, or understanding of high-performance distributed applications. And it's my pleasure this morning to introduce this year's recipient of the award, Dr. Rosa Badia. Dr. Badia earned the PhD in computer science in 1994 from the Technical University in Catalonia. She served as an associate professor at UPC from 1989 to 2008. And during some overlapping years there, she was involved in research at the European Center of Parallelism in Barcelona. And since 2005, she has been the manager of the Workflows and Distributed Computing Group at the Barcelona Computing Center, which is her current role. Her research focus over the years has been on programming models for complex systems, ranging from high-performance computers to clouds, grids, fogs, and today the edge. And some particularly notable contributions have been the development of the COMPS or PyCOMPS programming framework, which has been used around the world, and the OMPS task programming model, which has been highly influential on the OpenMP standard, also used around the world. Dr. Badia has been very active in the community, in conferences such as Supercomputing, Cluster, CC Grid, and of course, HPDC. And she's currently an associate editor for IEEE Transactions on Parallel and Distributed Systems. This isn't her first award. She's also received the Europar Achievement Award in 2019 and the Donatique Award for researchers in 2019. Today, she's going to present our keynote talk titled Superscalar Programming Models, a Perspective from Barcelona. So please join me in welcoming the recipient of the 2021 HPDC Achievement Award, Dr. Rosa Badia. I'll let you take it from here.
Thank you very much. It's really an honor to give such an award. Sorry. Always, of course, an award is always something very nice to receive, but in this case, when an award comes from the community where you do the research, it's even much more. Okay, I'd like to thank the support I've received from BSc and formerly at HPC from my directors and supervisors, but also from my research groups, as you mentioned, the Workflows and Distributed Computing Group, but also the Programming Models Group, where I was doing also the research on the OMPSs and others. Okay. So having said this, I'd like to start my presentation. I'll share the screen. I'll use, okay, now, okay, I'm now using, okay, I think you can see my slides now.
Yes.
Thank you, Anna. Okay, so, well, I receiving this achieve, which is for the contribution along the years, I thought that what would be nice is to present this evolution of the programming models. Okay, and so first I'd like to explain where this came from, no? And to remember the origins. No? So there was this Permas finite element method package from a company called Intes in Germany, and around 1994, Jesus Labarta was working with them, okay, trying to parallelize this software in the PermParm project, okay. So they considered different alternatives. One of them was the traditional physical domain decomposition, and then parallelizing the different decompositions of the domain in parallel and then merging the results. But in fact, what they implemented is a different approach based on using a data structure that was a hypermatrix with 3 levels. Since the matrices were sparse, each of the elements of the hypermatrix will have a link that would be null if the block was empty, it was zeros. And if not, it will have a pointing to another level of the matrix, and so on. And then the code stayed sequential, but when invoking an operation to a block matrix, this will generate a task, and a task graph was generated at execution time, and there was a runtime, a parallel task manager, that was parallelizing this block matrix operation, following what we know today as the task-based programming models or superscalar programming models. Okay, so and after this experience that was quite early, as I told you, when I started to collaborate with Jesus at the year 1999, he was always telling me, we were doing other related research, but he was always telling me, you need to develop the model. You need to develop the model. And so this is where it comes from. Okay. And what is the model? No? Well, the idea is that it's based on the superscalar processor. Everybody, well, in this audience, of course, know what is a superscalar processor. So you have a sequential list of instructions, of assembly instructions. And although the developer may think that this is executed one instruction after the other, in fact, what we have is that there are executions out of order. There are multiple parts of the instruction executed at the same time in parallel, because we have multiple functional units. There is things like renaming, etc., in order to run the application faster, okay, but always following having a correct result. No? So the change of order would never mean that you have an incorrect result at the end. So really inspired in this idea, we started to work on the superscalar programming models. No? And in our case, we based this on sequential programming using general purpose programming languages. Okay, so we are not proposing new programming languages, but we use annotations, decorators, IDLs to identify what task is going to be the task. And also we add the directionality of the parameters in order to be able at execution time to issue one task per annotated function, for example, and find the data dependency graph. No dependencies will exist. If one task needs the result of a previous one, there would be an edge between the two tasks. And then we have, traditionally, we have been working on runtime-based systems where the runtime is able to exploit the parallelism of the graph, okay, and make the different decisions, like the scheduling decisions, data transfers when needed, etc. Okay. Also, other characteristics of this programming model is that potentially you can have a large number of in-flight tasks. Okay, so although you may generate the tasks, usually you generate the task in order, not because you follow the sequential order of the application, but since there are the dependencies, it may happen that the tasks that start executing have been instantiated much later, exposing distant parallelism. Okay, and in addition, what we offer also is the illusion that there is a shared memory space or shared file system. Okay, by means of the runtime abstracting this storage or memory infrastructure, and similarly for the distributed computing infrastructure, okay, or for the parallel computing infrastructure. The programming model makes us abstraction, offers an abstraction layer to the applications. Okay. And this is a bit the chronology of the family of programming models that we've been working along these years. No? So from this PERM project, I started to work on grid computing. Okay, so for grid computing, we first proposed grid superscalar. Okay, and after this experience, it has some sons, I'll say, no. One is COM superscalar, still for the grid. Okay. And cell superscalar was specific for the cell processor at the moment. I think it was a very important processor at that time, okay, exposing many different aspects. In a way, a cell processor could be seen as a grid inside a processor, no, inside a core, inside a chip, sorry, because you have distributed memory inside and multiple parallel processors running at that. No? So the same ideas could be mapped into the cell processor. And also for multi-core, this was around the same time that multi-core processors started to appear. Okay, so we also developed SMPSS for multi-core, general purpose multi-core processors. So this line here is the distributed computing part, basically based on COMS, where we have been then moved to the cloud, and later also to with PyComs to try to do the conversions between HPC, big data, and artificial intelligence, and now also working on this edge to cloud environments that was mentioned. Okay, so this is what I will mainly describe more in these slides, in the next slides. But in parallel, also what we worked was with GPU Superscalar, hybrid models like this one that was combining parallelism at the multi-core level with the parallelism of the cell processor. And later on, we had another version of SMPSS that was had more advanced features. Okay. In parallel to this line, there were other efforts previously. This was CEPA. CEPA was before BSc. Okay, we were working at the university in this institution called CEPA. Okay, so there was this other project, Parascope, that was developing. No, Parascope was a more wide project, but we were working on DDT, which aim at do automatic parallelization of Fortran loops. Okay. And after this, also our colleagues work with Nanos, a runtime that was an implementation of the Nanos threads programming model. Okay, and from this we had this Nanos++, was the evolution of Nanos, and the Mercurium compiler, which merged together with the ideas of SMPSS, becoming of OMPSS. Now, OMPSS has been the instrument that we have used to propose new ideas for OpenMP. All the tasking ideas in OpenMP, dependencies, accelerators, we've been developing them on the environment of this infrastructure and then proposing it to the standardization activities. Okay, and currently OMPSS has been evolving into OMPSS2, okay, which is the current infrastructure. So together with COMS, now we have these two infrastructures, COMS and OMS2, as the stable infrastructure after all this evolution. Okay. Okay, so as I say, I will continue also on this top branch here of the distributed computing aspects. No? So what was Grid Superscalar? Was implementing the programming model that I was mentioning before, no? Based on the task generation of the task graph, but for C++ applications, identifying the tasks as functions using a core by IDL file. This was just by accident because we find this as a good way of using. And we were not based on compiler, it was based on code generation. From this IDL file, we were generating some application stubs, both for the part of the master program that will build a task graph and coordinate execution, and also some part for the worker side, okay? And it was also, it needed a small API, both for task submission, for synchronization, etc. In this case, was thought for coarse granularity tasks because the overheads on the grid were quite high, okay? So we were working with applications that were combining simulations or external binary executions. And in this case, also the parameters between that were exchanged by the task were files, okay? And had quite a powerful runtime, okay? Besides generating the task graph, was doing all the scheduling, managing the required data transfers between the nodes of the grid, doing renaming. So renaming is the technique import from register renaming in computer architecture, where you give different names to the same to different instances of the same file. No? And it had also checkpointing, fault tolerance, multiple features. Internally, we were using middleware that was used at that time, no? Globus Toolkit, in this case, Globus Toolkit 2 for job submission. Okay, when we had the tasks here developed in the task graph, they were submitted for execution to the workers in the grid through the GT2 interface, and also for doing the data transfer between the distributed nodes of the infrastructure. Okay. Also, we did another version that where we were using SSH and SCP in order to reduce the overheads that we had in the grid, in order to work with large clusters where the needs for security and distribution that Globus was offering were not needed. Okay, and this was in production during some years in Mare Nostrum 1 and Mare Nostrum 2. Okay, this is a sample application that we developed on top of Grid Superscalar. Okay, It is the fast DNA ML application. This application that does an estimation of the phylogenies based on maximum likelihood criterion was, we find it out because a collaboration with a group of partners, between them Indiana University, that we participated in a HPC challenge contest in supercomputing 2003. And we won the most distributed application award. Okay? This application in this case was based on MPI, okay? Particularly on the PAX MPI implementation, where our colleagues of HLRS were working at. Okay? And what we decided to, after this experience, to say, okay, let's port this version of FastML into Grid Superscalar and compare performance. Okay, we started with a sequential version. We defined the task that was the one that was evaluating parts of the phylogeny. Okay, but that was exposing some parallelism. No? The parallelism that we find had such configuration where we had some fork join parallelism. Okay, so was working for some evaluations of this function, and that there was some checking of the results that was required, that need the barrier here, and then opening again parallelism. Okay, so we did this application, and we compare with the two versions that I was mentioning before. The one based on Globus, and the other one that was running directly on top of SSH and SCP. Okay, and in all cases, understand that we were running in a distributed grid. And the flooding of the task was done from one node to another and going through the job scheduler. So the overheads were quite huge in this application, okay? in the scenario of these applications. We ran it with some work, some nodes of the TEMPA that we welded what we call a TEMPA grid, and also in another grid between Madrid and Barcelona with a larger number of nodes. Okay. So the results here are a bit mixed between these two infrastructures, but basically with PAX MPI, the latency in both cases was around 10,000 seconds. Okay, so here is time, so less is better. With Globus, we did first execution where we were quite disappointed because it was more than 3 times slower than the PAX MPI implementation. No? But we realized that due to this fork join schema, the slower nodes were defining the execution of each stage. Okay, so then when we did another execution using only faster nodes, even here we had less nodes than here, but the global execution was faster. And later also we tried with another configuration with the SSH-based version that was getting rid of some overheads, and we were surprised that the results in this case were faster than the MPI version. Okay, so this was one of the experience we had. No, and then after we continued working in the grid, but the core grid project appeared. No, core grid project, maybe some of you in the audience will remember, was a very interesting project at the European level. Was called a Network of Excellence. Was composed, I think, around 80 partners from all parts in Europe doing collaborative research. Okay, and a lot of the research, there was a lot of emphasis on the grid component model. Okay, some partners were working on it, and in this case, for example, the proactive implementation that came from INRIA in France. Okay, so we decided to do this re-implementation of Grid Superscalar on top of the grid component model, trying to leverage the characteristics of this component model, okay, to separate the concerns between the different elements of the runtime. In this case, the language that was used is Java, okay, because Proactive was working with Java. And an extension was that the task parameters could be files, but also objects in memory. Okay, so the task would exchange the objects, and the code, thanks to the use of JavaSys that is instrumenting the whole code, remains without any specific call to API. You have to identify the tasks and the data that is an input or an output, but then no other call to the runtime API was required. Okay, and for the middleware for the grid, we were using JavaGAT, which is the former or one of the instantiations of the Saga standard that OGF and OGGF was defining. Okay, so we were using this for job submission and file transfer. And here is another example of an application. It's Hammer, in this case, the parallelization of the HMP FAM tool, which is a sequence analysis tool. Okay. In this case, we did a parallelization using a space, the tool of a Hammer analysis suite that was sequential. So we were working with a strategy of splitting the input sequence into chunks, and also splitting the database against you need to compare these sequences also in fragments. And then having one of these tasks doing the HMP FAM for each chunk and div it per fragment. Okay. And well, the task graph had such a configuration in form of an inverted tree. Okay. This was run in Mare Nostrum 2, for example, using dual core nodes. Okay. And we compare also in this case against an MPI version. Okay, this case is an execution, not in the grid, but in a cluster, comparing an MPI Hammer, which is the line below. Again, this is, this is a speed up, so more is better. But the comparison is fair because the baseline we were using here is the same, was the execution in a sequential case. Okay, so we were using the same baseline in both cases. And comps was faster and also scaling quite better. Okay. And the nice thing also of this was that users from the EBI that were users of this tool use it in production in Mare Nostrum 2 for some of their analysis. And comps continued to evolution. No? So after the grid, it came the cloud. No? And what we did for the cloud, we had worked a lot in interoperability in the cloud. Okay, so comps now and at that time offered support for federated clouds and could work with different clouds, both public or private clouds. Okay, and we also developed elasticity in the cloud. So the fact that if the task graph was growing in a given moment and we need more computation load, we could add nodes to the infrastructure dynamically or remove them when they are not needed anymore. And we implemented some policies, both that were taking into account the time, but also the cost. In case of using public clouds, the cost of opening a new instance in Amazon or in another public cloud. Okay? And in this case, the same runtime can be used for the cloud or for the clusters. And what happens is that usually the applications that fit in the cloud require larger granularity tasks. Okay? So if not, the overheads will prevent good performance. And in the cluster, then we can cope with the smaller granularity tasks. And another addition at that time was the fact that some of the tasks could be deployed as services. For this, here we have an example of the IDL that we use in Java. So a regular task will be annotated with this add method. Okay. But if the task is in a service that has been deployed in a given URL and available here, it's annotated this way. And from the main program, you can invoke indistinctly one service or a method in the code, no? And the system is able to manage this. And in addition, also the whole application can be deployed as a service, okay? And then it can be seen as a service that is deployed in the cloud that is able to orchestrate workflows in the cloud. Okay. Another feature that we like to highlight here is the support for task constraints. No? What is a task constraint? It's, for example, in this case, that this task may require a given amount of memory in the node where it's going to be run, okay? Or a given number of cores. Okay? This is used at execution time to make sure that the node where we allocate this task has this given hardware in this case, but can be also used for software availability, libraries that cannot be installed in some nodes or where you need the license, etc. Okay. And another example of application, it's guidance. Guidance is a tool for genome-wide association studies. This has been defined by our department at BSc. So it's really from the life science department at BSc, sorry. And it's really a tool for their research, okay? In this case, they have used it for the identification of which genetic variants are responsible for some diseases, okay? Especially it's used for rare diseases. And for example, there was a study on the type 2 diabetes, or recently there has been these other studies related to age-related diseases, okay? This has published, for example, recently, this last study on the mature communications, and the same for the type 2 diabetes, they had another paper in the same journal. And this is from, as I said, from our life science department, and also in collaboration with the Broad Institute and other partners. Okay? Internally, an interesting aspect of this application is that it does extensive usage of the constraints interface, especially because this is a pipeline that orchestrates multiple external binaries. Okay, and these binaries, although most of them are sequential, sometimes they require a large amount of memory. So it was very good to have this constraints interface, because if not, here it would be, for example, the timeline. So here is the time, and different colors represents different type of tasks. This would have been the time that you require if you execute the application without an asynchronous programming model, where you have to insert barriers between the different stages, for example. And also if you cannot take into account these memory requirements, constraints, okay? And in case you can't get rid of the barriers, this would be an asynchronous execution. But then here, for example, what we did, we used then the constraints in memory. Now we can allocate for each task really the part of the node that is required, okay? Being able to better exploiting the infrastructure, okay? And finally, this is combining both asynchronous execution with the constraints for the memory. So we can see here that these features of the model enables up to 2x speed up in this case. And this is quite a large execution. It's for almost 3,000 subjects, individuals, no? Creating around 100,000 tasks and involving, as I said, this is calling a lot of external binaries, and then the data goes always through files, okay? More than 100,000 files. Okay? This was run, for example, here with 30 Marinostrum nodes, which is around 1,500 cores. And well, more recently, we have been working with Python, no? And why Python, no? So we decided to start to work on Python because it's the language that intersects between the HPC world and the big data and artificial intelligence. No? If you look at the languages that are more used in HPC, Fortran C, but also Python, mostly for scripting, but at least is not seen as something not usable. But then we have that in AI and big data, the use of Python is really intensive, no? And we have seen that other research groups have done the same decision. No? So we did this Python binding. It's the same runtime in Java. Okay, the comms runtime is the same with evolution that I will mention now, but it's still the same runtime. But we have a component that performs the binding between the Python and the Java runtime. And in this case, how we say what is a task changes a bit. It's in form of decorators that can be used in line. In the other case, for Java and C, it's used with an external IDL file. Here we can have the annotations in line, but we require, in difference to Java, a smaller API for synchronization. So we need the developer to add the barriers or synchronization for data in the code. Besides this extension of the language, for the runtime, there has been a lot of different improvements along the time. In the initial runtimes, what we had is that each worker will be instantiated per task. So remember that we were talking about the grid using globus and large overheads. So the worker were instantiated, started, execute the task, and they were finished. It was a process that was living very short time. But now we are working with persistent workers, both in the grid, well, the grid is less used, but in the cloud and in clusters. And we have then a communication layer that communicates the main program where we run the master and the runtime with the workers that run the task. And we have a worker per node, which is responsible for running multiple tasks at a time. Okay, for example, in Mare Nostrum 4, if we have 48 cores, it can run up to 48 sequential tasks at a time. Okay. Other extensions have been, for example, the integration with persistent storage. This means that data that is in memory can be made persistent and can be made available during the execution to other processes, or can be available after execution instead of writing into a file. And for this, we leverage some libraries developed at BSc, also Dataclay and Ecuba, okay, that deal with this issue. And okay, so this is a bit the evolution. Other things that we've been doing in the recent years. We wanted comms to be kind of orchestrator for complex workflows that can involve other programming models. So the tasks does not necessarily have to be sequential. Okay, a task in comms can be multi-core or multi-node. And with multi-core can be, for example, implemented with threads or implemented with OpenMP or OMS. And multi-node, it can be that the task is an MPI application. It means then that the workflow in comms can involve, for example, a set of MPI applications, and then later some tasks that do some analysis, and maybe these are sequential tasks or multi-core, another type of task. Okay. So for this, we have explicit annotations to program this. In this case, an example of a task that is an MPI application. For example, it has been used in this application, NMMD Monarch, which is an atmospheric task workers tool developed at our Earth Science department. Other things that we have extended, some of them thanks to the feedback of our users. In a lot of times, these large workflows run for a lot of tasks, and the users say, "Oh, in fact, I don't care if it's a set of tasks fail. Okay, you can just ignore. You don't need, because before we were stopping the whole workflow if there was a failure. So now you can, the programmer can say, okay, ignore that this task fails. If it fails, don't worry, continue the execution. Or you can say, ignore, but also cancel its subsections, because maybe it has some tasks that depend on this task. So you can cancel a whole part of the workflow. Another thing that makes the runtime or the environment very dynamic is this possibility of throwing comms exceptions from a task. It means that it can be that you are checking a convergence factor or looking if there are some results. Then a task can throw an exception to the main program that when captured can define what to do. And what to do can be canceling some tasks that are in flight, generating a new part of the workflow, things like this, okay? Making very dynamic the task generation. Other things that we have done is, for example, extensions for data streams. Okay, it's the data traditionally in comms was data that came as inputs, then we do some computation, and then we generate an output or a given set of outputs, but just one shot. So the possibility now is this, that a task can receive a stream of data, and this task then will remain kind of persistent while the stream is still open. Okay, when the stream is closed, then we will close this task. So we can now combine this new type of task that we call data flow tasks with the traditional task flow approach. We can have both things, and this can be, for example, used in scenarios of edge to cloud, where you can have a camera acquiring information in form of a stream of data and then generating some task flow tasks. Okay, and another example of things that we've been doing is the support for I/O tasks. In some cases, there are applications where you have some tasks that are intensive in I/O, writing to files or whatever, and I'm not using the computing resources. So by annotating this as in this case as an I/O task, what it enables is that these I/O tasks, in this case are these red tasks that here are sequentialized after the computation task, can be run in parallel with the computation task. This would be an ideal case where we consider that all of them can run in parallel. But using the constraints interface, you can also give constraints on bandwidth to the task, saying, okay, this is the estimation of the bandwidth that this task is using, and then the runtime can be more precise on scheduling the number of IO tasks that can run at a time. Okay, or even more, our student has been working on a dynamic auto-tuning of this bandwidth constraint, so the user doesn't have to do this estimation. It will be at the execution time that the runtime will be able to define this and after doing some evaluations, decide which is the best value. Okay. Other extensions have been more on the changes of the infrastructure that is now requiring us as the support for containers. No, some communities are really interested on having their applications in containers, the whole application, or even the small parts of the application. No? And we support both. You can have the whole application in a container or individual tasks in a container. So then you can see the comms as an orchestrator of tasks in containers. And also we support elasticity in this case also, okay? And this can run both in cluster with Singularity, for example, or in clouds with Docker or with other cluster, other the container engines, okay? Again, it's based on an annotation, okay? In this case, for the defining that a task is in a container, you have to add this add container annotation, for example. And well, a bit to wrap up this part of the comms environment, it's not only the programming model and the runtime, it also comes with a set of tools to help the developer and us as runtime and programming model experts. One is based on the Paraver environment, which is a tool provided by another group at BSc, which is enables a very in-depth performance analysis, okay, based on postmortem traces. Okay, so the nice thing is that from comms you can just setting a flag generate a Paraver trace file, and then you can have different views. This, for example, is a view of the tasks, no more at the programmer level, but also we can have views on the runtime. So for us, it's also very useful to be able to fine-tune the runtime. Another is a monitor. This is a web-based application where you can plot the graph dynamically, how it's produced, how it's been consumed, the number of infrastructure nodes that are on. If it's in the case of the cloud, that nodes can be added and removed, for example, statistics about the tasks. Okay, this is very useful for demonstration and also in project reviews, for example, no? Where it's nice to show the reviewers what you've been doing. Another very interesting tool for the users is the fact that we have integrated the Jupyter notebooks with our runtime. So you can have the comms applications in a Jupyter notebook. Can be used, mostly we use it for training and demonstration also, but it can be used in production. You can write your own application as a Jupyter notebook. Okay. And well, this is another example of application that we recently have been working in the framework of the Execute project. Now, this is more on the HPC area for manufacturing, and they have been working on methods for uncertainty quantification, okay, using multiphysics and multiscale problems. In this case, the workflows that are written on top of PyComs combine simulations of MPI simulations with a Kratos multiphysics solver. Also invocations to the MMNG measure that performs adaptive mesh refinement. And the orchestration is based on a Monte Carlo library that performs a multi-level Monte Carlo evaluation. No? And our colleagues in this project have been working, for example, on analyzing the fact of that thanks to the behavior of comms or PyComs, the synchronicity, they can develop asynchronous Monte Carlo workflows. Okay? And the scalability, this is in Mare Nostrum 4, is quite well. In this case, almost ideal scalability for a use case on wind engineering that they are using in the project, no? That analyzing the impact of winds in buildings on a city, for example. Okay. Okay, so then the other aspect that we've been working is in the evolution towards this computing continuum that has been called, no? Or at the beginning we were calling of edge to cloud or edge fog to cloud. Basically, when we were started to working in this environment, what we saw is that we could not work with the centralized runtime that we have been working until then. Okay? So we needed to work on an approach where the runtime has been decentralized. Okay, and in each of the nodes, where the nodes can be a mobile, can be a processor in a car, etc., or in the cloud, each of them will have a whole comms runtime. Okay, and then you can initiate a computation in each of the different levels of this infrastructure. Okay? And then the nodes, for example, if it's a mobile and has a small computation capacity, can peer dynamically with other nodes, okay, to solve this problem that has been invoked at that level. Okay? And if necessary, it can offload up to the cloud if more computation is required. Here, another aspect is important is the management of the data, no? Because if these nodes can appear and disappear, we can have data that is lost. Okay? For this, we are using data play in a federate mode in the way that the data can be persisted in multiple nodes and be available if one of them disappears. Okay? This has been used in the MF2C project, okay? But also it has been applied in other projects like this one, Elastic, led by some other colleagues at BSc that have a use case of the Florence tramway. But they are using a use case of the prediction of the risk situations in the tram environment. So it uses information that comes from camera and tracks the movement of people, cars, and others, okay, around the tram environment, analyzing the situations. Okay, this is an example of the task graph that is generated with 1 second of execution with a single camera, for example. Okay. And well, I'm heading the last part of the presentation is about what we are doing now. No? And I'd like then to present a project for which I'm the PI. Okay. It's the eFlows for HPC project, which is one of the new Euro HPC projects. Okay. The Euro HPC aims to build the exascale HPC infrastructures in Europe and has also funding for projects that deal with other aspects, not only with the infrastructure. Okay. In this case, this project aims at developing a software stack for workflows that combine HPC, okay, with artificial intelligence and data analytics. Okay. And for this, we use different use cases from 3 different pillars, different communities. One from manufacturing, building digital twins for manufacturing. Another one on climate with adaptive workflows, for example, for tracking the evolution of tropical cyclones. Or another case from the urgent computing community for the detection of the possible impact of earthquakes and tsunamis. Okay? And all these use cases are linked to centers of excellence in Europe that try to give service to the community, in this case for manufacturing, for climate, or for urgent computing. No? And besides the software stack, what we would like to provide in the project is an interface for doing what we call the HPC workflows as a service. No? This means that these communities can develop their software, their workflows, and deploy them in a repository of workflows that can be then instantiated as a service for other users. Okay? The idea is to run them in federated HPC with a cloud that basically acts as auxiliary cloud to support some of the services that cannot be installed on the computing nodes of the HPC systems. No? Also, there is some task on architectural optimizations for new type of architecture or new type of devices, for example, for GPUs or for FPGAs, and also considering optimizations for the European processor. A bit, this is the architecture that we have been defining. Okay, this has been very recent work. We are just delivering this month. Okay. It's based on the combination of PyComs for the development of the workflows for this dynamicity and integration of HPC, data analytics, and AI that I was saying before. Also using Tosca, one version that they call extended Tosca, which is a standard for orchestration. No? In this case, this will be used to define how we need to deploy the applications at the beginning, the different components, how they need to be deployed and installed. And the data logistics pipelines will be used for defining the data that needs to be moved at the beginning, but also during the execution between the external storage and internal storage of the HPC and cloud systems. And then for developing the workflows that I was saying, we would like to have a set of catalogs and repositories and registry where the different software that is used, the models, this can be models that are already pre-trained, machine learning models that have been pre-trained and can be reused in the workflow, and also data that will be used. No? So with these components, the user will develop the workflow, okay, select these components and develop a workflow, and then register the workflow in a workflow registry that will return a workflow endpoint that can be used later for invocation. Okay, and then at invocation, we would use the ST orchestration for the deployment of the different components, performing automating installation of the workflow. The goal here is a bit to reduce the overhead of the installations in HPC, no? And reducing the learning step of the users that they have now on HPC systems. And then at the execution time, the dynamicity of the workflow will be dealt by PyComs. Okay? And in case of federation of different systems, we will use Unicore. Okay? Also, there will be some components for data management, the data logistics service that will perform the different movements between the external storages and internal, and Ecuba and Data Clay for the management of persistent data in the applications. So a bit to conclude the talk, we think that the concept of the Superscalar programming model has been proved to be valid, no? Both for parallel or for the multi-core or accelerators, no? That is more now on the ESS instance, or for distributed computing, which is more the COMS or PyComs installation instance. We have been doing multiple implementations, as you've seen, a whole family that have validated different ideas, but now are converging to these two different platforms. So with what we are maintaining at BSC right now, it's COMS with PyComs, which is the binding for Python, and OMPSS2. We consider that PyComs offers a programming platform that can be used at different levels, because you can use it for codes that are defining fine-grained tasks and can solve linear algebra codes or machine learning algorithms. We have a library called DSLib, for example, that has an interface in Python, similar to scikit-learn, but it's parallelized with Python. Okay, it can be used also for defining workflows that involve external binaries like MPI, and combining it with other smaller tasks that do, for example, data analytics. And this is a bit what we are trying to do in the flows for HPC project. Or it can be used in much more distributed computing environments where the scenarios are a bit different, no? Where maybe the workflows are not that big, but there is a lot of complexity in the terms of volatility of the components, on the security aspects, data persistency, and so on. Okay? Current efforts are on this integration of AI with big data and HPC workloads. Also on further development of this last version that I mentioned for the computing continuum, which, for example, offers the possibility of having task nesting, okay, tasks that are defined inside tasks, and other functionalities that are required in this other scenario. The integration with the function as a service paradigm, okay, to offer the same paradigm that we can find in the cloud, but integrated with task-based approach. Also in checkpointing and restart, and also in making easier the deployment of applications with this paradigm that we have called HPC workflows as a service. all that we develop is available as open source. Okay? You can find tutorials of comms and PyComs in YouTube, for example, and we have a web page with documentation, with the source code, but also virtual appliances and container images, etc. And also we have sample applications available in GitHub. And well, as you can imagine, it's not the work of a single person. I already said at the beginning, thanks to BSc directors and BSc support in general, but especially I would like to thank my group. And now it's the Workflows and Distributed Computing group. Before it was called Grid Computing and Clusters group. And also to the Programming Models group, where all the work around the OMPSS was developed. Okay? And also thanks to the funding that we have had along the time. Here are not the projects that we have been involved. These are the projects that are live now, with a lot of application in different communities in like life science or in manufacturing, or even in, this is for policies for the usage of the land, which is very interesting, and others more related to the actual developments of PyComs that I was mentioning. Okay. And well, thanks for HPDC for inviting me and for giving me this award. Hope we can meet in another edition in Stockholm or wherever. Thank you very much.